Yo, what's up, everyone? Good morning. It's Tuesday. That's my bad. um, we're just getting through, and really, I can't decide if we have 2 weeks or 3 weeks left of content. And the reason is like from here on out, we have like four. We have 4 or 5 more lessons. Let me just write that: 4 or 5 more, and they're all going to be kind of tricky because we're at the end of the year. We're at the hardest concepts. Um, And this concept for the next 2 or 3 lessons is called experiments, which are similar to learning about samples. Remember when we did a very, very brief, people didn't like it, and I don't really like it either, but very brief talking about random sampling, like systematic, that kind of thing. We have to talk about types of experiments too, and then also a new type of significance test and confidence interval, okay, which is called the two sample inference. I feel like I just said a lot of scattered thoughts, but hopefully it made sense. Um, but here's the plan. Today we're going to learn the math and the logic behind a two sample test and confidence interval. And then the next lesson is going to talk about setting up an experiment. So think that on the AP exam, we know the 4 step process for a significance test. You would have to add a 5th step for a lot of these, which is actually writing out how you would do your experiment. So that's what we're leading to next lesson. And it might take me 2 lessons to get through that. So we might end up doing this for the next 2 weeks. Either way, I'm not that worried because we have still 6 or 7 weeks till the AP exam. So we got some time. I think this is really complicated, but in the best way. I think this is really interesting. So hopefully you guys will think so as well. Let me read the question. It says that scientists are conducting an experiment on the effectiveness of 5 milligrams of melatonin on sleep for insomniacs. They take a random sample of 300 people and give half of them melatonin and half of them a placebo. They find that 32% of the melatonin sample have a better night of sleep and 24% of the placebo sample have a better night's sleep. So the first thing that you should just notice from this is that we have 2 samples, okay? There were 300 people. Think that 150 were given melatonin and 150 were given a placebo. And they don't know who is who, right? So they're going to take this pill and they're going to report how well they sleep. And they found that 32% had a better night's sleep, right? So what we would have done before is we would have taken the single sample 32%. And with that sample, we could find a confidence interval. We could say the true proportion is in between 28 and 35% or something like that. Or we could do a significance test where we test something like 30%, right? Is this greater than 30%? Certainly. And that's all good and well. But something that is going to be equally useful and something that you do in the real world is you might just want to test whether one sample is definitely or statistically significantly higher than the other sample. And I said that really poorly. But what I'm getting at is we want to find a p-value that tells us that melatonin definitely is better than the placebo. Okay, so we have these 2 samples, and rather than compare them to like 30%, some random number, you're going to compare them to each other. Okay, you're comparing samples to each other. That's the big thing with a 2 sample test. Okay, so the first thing is, what is the difference in samples and the standard deviation for the difference? So difference in samples is going to end up being the center of our sampling distribution for all of my math. Okay. And what I mean by that is, like, first, let's just calculate it, right? We can say the difference in proportions is P1 minus P2. Okay. The first one, and like think like how much greater was melatonin than placebo? It was 8%, right? So the first sample was 32, and the second sample was 24. So we could say the difference in samples was 8%. that the people who took melatonin had an 8% higher chance of getting a better night's sleep. Okay, so for the rest of this, when we do our test, 8% is going to be the center of the confidence interval, and it's going to be the data point that we compare to the mean, okay, or the center. Hopefully that makes sense. The difference in proportions is 0.08. And what you always have to remember with inference is that this isn't necessarily the true difference, right? That's just what happened in our samples. There is a true difference between sleeping with melatonin and not, but we don't know what that difference is. So we estimate it as 8%, right? This is our best guess. But because this isn't definitely the truth, we can find a standard deviation for the difference. Hopefully that makes sense, right? We want to know how likely it is to vary from this answer. So this is our new data point, just taking the two samples and subtracting, which isn't difficult. But now to find the standard deviation, we're going to learn a new formula. I'm going to put it on the next sheet, but I kind of got lazy. And it's the trickiest standard deviation formula we've done yet. But just think, like, the technique is the exact same. That's why I think stats is kind of easier than it looks, because there are 4 different standard deviations. This is the third one. And once you have the standard deviation, all the math is going to be the same. So let me just write it, and then we'll solve it. It's really predictable formula. Everything at the end of the year is pretty predictable, in my opinion. And it's P1, 1 minus P1 over N1. And then the same thing for P2, which is the second proportion. Think that it's just the standard deviation formula for a proportion twice, okay? And both times are inside the square root sign. So let me write the numbers in so that you see that it's very similar to before. P1 was 0.32. Then you just multiply it by the opposite percent, so 68%. N1 is the first sample size, which in this case we have to remember is 150, because there were 300 people total, split in half. The second one is 0.24 times 0.76, and also 150. So calculating the standard deviation is going to be the hardest part of a 2-sample test. And this standard deviation measures the spread of the difference. Okay, we're talking about the difference in samples now, and this is going to say one standard deviation away is 2% or 3%, something like that. And here I'm getting 0.051. I don't know what that noise is outside. Maybe you can't hear it, but yeah, that is my standard deviation. So hopefully, and I definitely think when I do the practices, you should be doing it as well. Make sure your calculator skills are strong, but that's our standard deviation. Hopefully everyone's on the same page as me. So a single sample, you would just take one sample and find a 1 standard deviation. The difference in samples, you find this harder standard deviation. So now let's move on to the actual math, but we've already done like a lot of it. For B, it says to create a significance test at the 5% level to test whether or not there's a significant difference between the placebo and the drug. So first, let's write some hypotheses. A lot of times I kind of stop writing all the steps once you get farther in, but the hypotheses are really important, okay? So first, we are testing whether or not there's a significant difference between the placebo and the drug, okay? So we want to test whether or not there is a difference. So the first thing to recognize is that the null hypothesis, instead of it being like P equals 30% or something like that, we're testing, is there a difference between the two of them? So remember, null hypothesis is what you want to reject or fail to reject. We're going to test if the difference between them is 0. Right? We're going to find a p-value that indicates whether 0.08 is far enough away from zero that there's a significant difference between the two samples. So the null hypothesis for a two-sample test is going to be that the difference is zero. Think that we're going to do 0.08 minus zero over the standard deviation. That's how we're going to find our z-score here. But the null hypothesis is that there is no difference, right? This is saying that P1 is 0.32 and P2 is also 0.32. There's no difference between them. So we're trying to reject or fail to reject that there's a difference between the two of them. And in this case, it's going to be a two-tailed test because we don't know which is going to be higher, right? It doesn't say to test whether the drug is higher. It's just saying that there's a difference between the two. And that might be the hardest part for people. But that's why we have it does not equal zero. What we're trying to figure out is there a difference between the samples, or can we go with the alternative? Or sorry, are the samples the same, or can we go with the alternative that they are not equal to each other? So that is how a two-sample test works. You would do conditions for both of them. So you'd say both the samples are random, both are greater than 30, you know? But now let's do the math itself. I think this is going pretty well for what I consider to be a difficult lesson. And like very, very quickly, I didn't really want to do this, but I just want to show you. Like I didn't want to spend too much time on it. Here's what we're doing. Another stupid normal distribution. We are testing that there's no difference with a sample difference of 0.08, right? So we are going to test the difference and see how big that percent is. We are going to multiply it by 2, and we're going to talk very briefly about like a negative in this case. But we want to test, is 0.08 far enough away from 0 that we can reject 0? Okay, that's the big thing for all significance tests, but that's kind of the visualization here. And what that means is if we want to find my z-score, figure out how far away this point is in context, the data point is 0.08 minus 0 over the standard deviation. So if you want to really think about it, minus 0 means that the z-score is just this number divided by this number. So I think that makes solving this actually pretty easy once you have your difference and your standard deviation, right? Is 0.08 far enough away from 0 that we're going to get a small p-value? So that's the math. 0 is what we're testing. 0.08 is what we found in the samples. So 0.08 minus 0.051. Crap, I did that wrong. 0.08 divided by 0.051. We're going to get a z of 1.57. And that is a z-score that is close to fail or reject, right? Anything that's like 3 or 4, easy reject. Anything less than 1, easy pass. Let me find my thing, okay. Bam. 1.57. 1.5. Wow. Wow. It's going to be so close, which makes me kind of happy. 1.57 is, and I know you can't see it, but is 0.9418. So P equals 1 minus that. And then we're going to multiply that by 2 because it's a two-tailed test, okay? And that always comes down to the hypotheses. And again, you could have set this up where P1 minus P2 is greater than 0, and that'd be a one-tailed test. But I'm just testing both sides of this, okay? 1 minus 0.194. So it's 0.0582. So a one-tail, it was actually going to pass or fail to reject anyway, because that's greater than 5%. But multiplying it by 2 kind of guarantees that we're going to fail to reject. So I think that's really interesting. Let's talk about that. P is greater than A, and A is the significance level. So it's 0.11 is greater than 0.05. So therefore, we fail to reject. Now let's talk about that, okay? So clearly this is a long lesson. That's why we'll probably take 2 weeks with this, and hopefully you're still with me. But what we determined is that even though there was an 8% difference between the two of them, that difference wasn't big enough to get a small enough p-value, okay? And that just was because the standard deviation was so big. So a bigger sample size would have made this smaller, and we probably would have rejected that they're equal. But in this case, the sample wasn't big enough, and we narrowly fail to reject, right? So when we fail to reject the null hypothesis, it's not saying we accept it, but it's saying that we're choosing this one over this one. We have no evidence that they're not equal to each other, okay? And that can be counterintuitive because you might say, well, there's an 8% difference. Clearly, there's a difference, but this difference isn't big enough that we think it's definitely different. And I know that sounds so stupid, but hopefully you guys are with me on that because it's the same logic as what we would do before. But again, the p-value was 11%, which means there's an 11% chance that this could occur even if the truth is that there's no difference. So that's high enough that we're going to say that it's possible. So that's a significance test. We haven't done those in a few weeks. Now let's do a confidence interval here. And we're going to do the exact same thing, okay? Where we're going to now take the difference of samples and create a confidence interval that says we are 95% confident that the true difference between them is in between this value and this value. And the good news is we literally did it, like the math already. And that's kind of why I put it in A by itself. So you understand that this is kind of fundamental to inference, okay? Whatever inference you do, whether it's a significance test or a confidence interval, you have to find your standard deviation, okay? And understand what you're testing, your data point. Anyway, I feel like I'm kind of rambling today. I'm sorry about that. But we have the sample difference is going to be the center. And then we have the critical value and the standard deviation. Okay, so 0.08 plus or minus a 95% confidence interval. You already know I have those numbers memorized. It's 1.96 for the critical value, and the standard deviation is 0.051. So really easy, right? 1.96 times 0.051. And we're not even going to do 99% because this worked out perfectly what I intended here. We have 0.08 plus or minus 0.09996, which is 1, 0.01. Let me just write that. 0.1. Okay, so we rounded it to 0.1. So we're going to do 0.08 minus 0.1, so negative 0.02, and then 0.08 plus 0.1, which is going to be 18%. Now, I want to interpret this together, and this did exactly what I wanted. So here's my confidence interval, and it's negative 2% to 18%. Okay, and first, that's a really big confidence interval. Maybe something that we can take away from this together is that even 300 people in an experiment is not going to give you a small enough standard deviation to make real inference, right? 300 might be good enough for a 1 sample test, but for a 2 sample test, it seems like it's making the standard deviation too big, because this spread is 20%, right? Where it's saying when 95% confident the true difference between melatonin and the placebo is negative 2% and 18%. So what does negative 2% mean? And maybe pause it to think, because it's definitely gettable. But remember that we were doing P1 minus P2, right? The difference in samples. So if the difference in samples is negative 0.02, that just means that P2 is 2% greater than P1, right? It means that P2 minus P1 is 2%. So if you get a negative confidence interval, and that happened on the quiz accidentally, that's actually like, if you're here, know that that's like not really allowed or good for a 1 sample test. But if you get a negative for a 2 sample test, what that is going to indicate is that the second sample is actually bigger than the first, right? It's possible that P2 is as much as 2% higher than P1 within our confidence interval, okay? And even if I didn't say that perfectly out loud, I hope that makes sense. But the range here is we're 95% confident that P2 isn't any greater than 2% higher than P1, right? It's not like the placebo is 3% or 4% or 5% higher. The most it can be higher is 2%, all the way to melatonin working at 18% more than the placebo. Okay, so that's what a negative indicates, and negatives usually will indicate failed or rejects, because part of your confidence interval is the other way, right? We're testing that the difference is 0, so both sides of 0 were included in my confidence interval, right? Negative 0.02 all the way to 0.18. So I didn't really write any of that down, but the logic of that is kind of the most important part. So yeah, I'm happy we finished this one. Definitely one of the trickier lessons. We just covered all of 2 sample tests with a proportion, and hopefully it's clear. So I think where we're headed is 2 more experiment lessons, but I haven't really decided. But I appreciate you for being here. Good work.